Hello everyone, welcome to the CVPR 2020 tutorial in synchronization and cycle consistency in computer vision. I'm Tolga Birdal. I am co-organizing this tutorial together with Federica Arrigoni, Chixing Huang and Leo Gibas. I will make an introduction to this topic, and deeper specializations will be explained by Federica, Chixing and Leo in different domains. Let us begin with the very definition of synchronization. What is synchronization? It's basically the coordination of events to operate a system in unison. It's finding simultaneity in any quantity we like. From daily life, like let's synchronize our progress, to music and to time, synchronization is actually used everywhere. And it all began with clock synchronization. There's this beautiful book by Peter Gallison. It's called Einstein's Clocks and Poincaré's Maps. It lays out a very nice, fundamental, and easy to follow picture of the history of synchronization. Of course, it's in context of clocks. It all began with the efforts to standardize the units we use, called the metric system. And the very definition of the entities are now in France, because this is where France became the center of the metric system. And if you think about it, kilogram, for instance, is an absolute quantity that we could take. We could define a kilogram, we could measure it by a piece of metal, and we can define it as a kilogram. And doing it for time, which is a relative quantity as proven by Einstein, is very, very difficult. And it took a lot of efforts to standardize time, even if we standardize the metric system. So how do we standardize time then? Well, it's a funny story, because the initial attempts involved certain mechanical systems, like pneumatic pipes, pumping time from a central clock in Paris to the rest of the clocks in the city. And that central time, of course a local time, because universal time didn't exist back then, was accepted to be true time, and the others were mechanically signaled to calibrate with respect to that. And that's quite funny. Because it's just not feasible to apply this universally, right? So how would we do it after the invention of long cables and electronic connections, or telephones and telegraph? We could basically use some better algorithms that benefit from relativity, which Einstein proposed, right? And he was in Bern, and that was a city which was in no shortage of clocks back then. And the first synchronization algorithm is known to be the Einstein-Poincaré synchronization. So Poincaré is a polymath in France. He has a lot of influence in the world of mathematics, involving the very work of Einstein. So how they achieved this task is as follows. They basically took time at A, right? So the goal here is to figure out the time in B with respect to the time in A. And what we could do, we could send a light signal from A to B and then measure it back. And then measure the time difference at A. Well, this is relative to the starting point of A anyway, so we can measure this. And then set the midpoint of this to be the clock at B. This is called an Einstein-Poincaré synchronization. Since then, it has been applied to many places, including wireless communication and language translation, that they all use some form of a synchronization. Of course, the initial algorithm of Einstein and Poincaré has been largely modified and developed to operate in those, let's say, more scaled systems. Naturally, after all those developments, it leaps into computer vision. And then we speak of cycle consistency, which is essentially a consistency that is imposed by synchronization, and synchronization itself in computer vision in the systems that we use today. So what are those examples? Well, basically, we could just take the idea of translation, and instead of translating language, now we can translate images that could go from one style to the other, you know, like from a Monet painting to a Van Gogh painting, or we could go from a CT to MRI, different modalities in medical imaging. Right? Or we could process videos. We could understand time as a flowing quantity, and then we would like to synchronize those frames that we see in time. We could go to 3D registration in multiview scenarios, right? There should be a coherence of observations in the real world. We could go to video translation or motion retargeting, right? So transferring the motion of one character to the other. Or we could just go to more fancy things like generative modeling, deformation, and all that. Of course, we could completely work on different modalities. There is basically no imposition of cycle consistency to be connected to images or whatnot. And one is FlowNet, for instance, that uses consistency to estimate scene flow, or there are other algorithms that use it to estimate deformations or 3D registration or rigid pose and so on. Then comes synchronization. That's basically a giant form of cycle consistency in a graph. And whenever we have multiple quantities or multiple observations that somehow relate to one another with certain pairwise information, we could use the cycle consistency in different regions of the graph to ensure the consistency of the entire graph. So from structure from motion, where we naturally have multiple images, to segmentation, co-segmentation, for instance, there are many applications in today's world. And the most successful algorithms, as you see, these are all recent works, benefit from some form of consistency. So let me introduce some notation to begin with. I will be speaking of a graph that is composed of certain vertices and edges. And the vertices, we could think of it as a set. And each vertex is associated a domain. That's a domain where a quantity is stored per vertex, right? It could be images, it could be camera poses, anything, really. And between domains, we can think of these relative maps. So we could think of those as transformations which take one domain to the other. And then we can speak of a vertex labeling, where each vertex, at each domain. So I can think of a function that basically maps the domain, maps the vertex to the domain. Now, going into a bit of the details in a graph. So you see below, there's an illustration. So the colors are encoding correspondence, and a path basically is defined as a set of connected edges that is transforming one vertex to the other one. So, right? So to basically traverse the graph, we could follow paths. And what we call a cycle, if the path goes back to the vertex that it started. So here in this scenario, we are simply adding back the original I1 into the list of vertices that we traverse. And we will call a null cycle a cycle along which I chain the transformations and arrive at the identity. So basically, I haven't done anything, right? So I started from one vertex, from vertex 1, and then went to vertex 2, to 2, to 3, and then at the end I come back to 1, and if I chain all these transformations, they will just give me the null cycle, the null transformation. And if you think about it, one cycle is going from the vertex to itself is actually it has to be a null cycle all the time, right? So because this is always an identity transformation somehow. And two cycle is just going from ij and I to j, and then back to I from j. Right? That's called the two cycle, and these are two special cases. Right? Cool. And I will define another entity which is less known in computer vision, which path invariance, and the importance of this is understood recently with the neural networks especially. So let's have a look at the difference. Let's imagine all possible paths between a vertex u and vertex v. I will denote it as gpath uv. And let's say all possible path pairs. So if I were to take all the pairwise combinations of the paths, right? So all uv, such that there is a path from P to Q. So if I unite all those, that's all possible path pairs, right? I will say G pairs for that. And then I will call a graph to be a path invariant one if for any path that goes from P to Q, right? So if I basically take, so any path that takes vertex U to vertex V, I will say that there is path FP, there is path P, and there is path Q in path pairs, and they should lead to the same result always, right? And I will say if it's cycle consistent if any cycle that I take from the set of cycles in the graph, I end up at the null side, the null transformation, right? So I end up at the identity map. So the difference is the following: in this graph, there are cycles, right? There's basically one cycle going like that. We can think about from I to J, J to K, and then back to I. This is like an undirected graph if you want. And along this cycle, to have a cycle consistent, to have cycle consistency, basically I should be starting from vertex I, going back to vertex I, chaining the transformations, and arriving at the identity map. However, if you look at the graph on the right, basically I have now 3 edges. Now this is a directed graph, and if I follow this path of purple versus this path of blue, I could end up at the same VKs, at the same vertex, or at the same result. However, now there is no cycle in this graph, so we cannot really speak of cycles. So what I actually want is that this path and this path would give me the same result, so the same quantity. And this is called path invariance. And the distinction is quite important actually. So I have been speaking of these Fs, and these, of course, we can have certain assumptions on them, right? So we can generally observe what computer vision people use and kind of, you know, derive conclusions from this. So first of all, it's very common to have an isomorphism, right? So if I'm going from I to J and then coming back to J to I, it's likely that I can take IJ and invert it. And these maps are often linear, so think about it. It's the rotation matrices, you know, all those maps from let's say one set of vertices to the other one can be like a subgroup of permutations, for instance, and anything really. And Fij could be group valued, so it could have more things than invertibility, like it could be closed, associative, and so on. And under this scenario, if I'm able to write Fij as this operation, so Fi, kind of the group operation, let's say just times for the moment, and Fj inverse, I should be ending up at the same relative transformation. And if that is satisfied for all the edges, then I'm basically creating a consistent vertex labeling, and this is also in alignment with my observation or with what is given in the relative transformations or relative maps. So this is by construction a cycle consistent graph, and the proof is very simple actually. So if I take the definition of cycle consistency and just plug this in, right, for all I and j's, I am basically ending up at the null cycle. So indeed, that's a cycle consistent graph. There is a catch though. This entire formulation is subject to what is called a gauge freedom that explains the conventionality of simultaneity. Think of it as follows. Formally, I can apply this Fg, any arbitrary transformation that is in the group, to all these absolute maps that I either estimated or defined or constructed, and the cycle consistency would still hold. Just everything would hold the same way. So I will be consistent with the Fij's of my data, right? So I can basically fix any of those functions. Like for instance, I can fix Fi to be any Fj, right? So to be an identity, for instance, if that is the case, and just get rid of this gauge freedom. There are better algorithms to get rid of gauge freedom, and this is completely problem specific, I would say. And this is also very well explained and very well grounded in theory of relativity, which is justified by these words of Einstein. So what are those maps really? I have been talking about those maps. What are they? Well, we see them everywhere in computer vision. from estimation of rotations to estimation of correspondences, or multiple quantities such as segmentation and rotations and correspondences, to neural networks, right? So these maps could be really, really complex indeed. So we don't have many assumptions on them. Well, certain formulations, of course, admit linearity, but as a general principle, we do not require that. So you see here that it opens the door to many applications, thinking about the maps as general quantities. I will begin with cycle consistency and path invariance, and then slowly move to synchronization. So we have generally, in a machine learning scenario, we have those supervised learning problems where there's an input, xi, and there's an expected outcome, yi. And during training, we see those labels yi, and we try to map xi to yi. So we try to learn a function to map one domain to the other. And this is very well defined, because for each input, there's an output, and I just learn this function. It's one-to-one in that sense. However, in many unsupervised scenarios, I am given a complete data set which is unlabeled, and another label set which I would like to map my input set, right? So this we could think in terms of distributions, or in terms of figuring out what the map would be, and figuring out the correspondences between them, right? These are different problems, and cycle consistency and path invariance are mostly useful in the latter, in unsupervised scenarios. So they are generally loss functions. Let us analyze some of the recent computer vision papers in the framework that I have just described before. So let's begin with CycleGAN. The task here is to map a horse to a zebra, and really how a CycleGAN is trained is through a cycle consistency constraint where we map from one domain to the other and back, and we want to arrive at the same place. And in terms of the graphs that I have been showing, this can be explained by such a simple graph, right? Where we know the nodes and we want to figure out the relative transformations in between. And we are instead of seeking a vertex labeling here, we are seeking the relative maps. But here on the right side, learning dense correspondences via 3D guided cycle consistency, the task is to consistently find correspondences across images. And to do so, there's an intermediate supervision, an unsupervised one rather, or let's say weakly supervised, that from the real image, we go to the synthetic version and then map between the synthetic views of two images, and then come back to the image in another viewpoint or domain, and so on. And this can be expressed in such a graph. So, but you see in that graph, we are essentially first performing a map between two real images, and then we are walking over the synthetic images, come back to that real image, and we want a consistency here. Essentially, that's a path invariance, because there is no cycle in this graph, right? And same thing can be said in another application where we would like to do some expression transfer or phase correspondence estimation, whatnot. We go again so we go to 3D and map back to the 2D of another view or expression, and there is the same identical path invariance going on here as well. Let's come to this unsupervised video interpolation example of Reda et al. It's quite interesting application where we have a video. I'm showing 3 frames here, and from 2 of these frames, I'm learning a neural network to generate an intermediary frame, and from the other 2, I'm applying the same. I'm learning an intermediary frame as well, and then I'm using those frames in the same neural network to come back to the observation that I would like to have here. Right, so I want that the images that I synthesized can synthesize back the frame in the middle, Well, this could be shown in such a graph. Similarly, a similar story here. So the known things are marked in green. So the colors are corresponding to the frames here. And then we have such a small graph where we are actually having a path invariance. We are arriving at the same node, but through different paths. So, and that doesn't actually create a cycle. Right, but all these things are said to be cycle consistency in computer vision because, you know, different interpretations can view them as cycles actually. And note that here we are again given these nodes, and we are trying to figure out the maps, the relative maps in between. And now let's move on to another application, which is quite interesting. It's a style transfer one. So here I'm having two images, or I can have more, and I will be starting from the first, and I generate two codes, content and style, and then I can take one content code and randomize the style, yielding another image, and that image I desire to have lie in the domain of another image. This could be cats, this could be dogs, or any other, you know, style transfer problem that you can think of actually. And I do the same operation to this image as well, and the generated image should lie back in the domain of this one. And here there are multiple cycles and going on in multiple places, and I can have way more, you know. And so basically, our losses could be a mixture of cycle consistency and path invariance. And there is no strict requirement that I have to pick one. There could be, you know, depending on the graph, there could be multiple versions of those. And recently, there are great advances using path invariance. So we have an input, let's say model or an image, and we have a desired output, right? However, there are many ways to go from an input to the output, right? I can follow many paths. I could first create a volumetric reconstruction and then map it to the segmentation, for instance, or I could create a point cloud from it. I could create multiple depth images and viewpoints and all these things. But in the end of every path, and by the way, every edge here is a neural network. And even in such a complicated graph, I want a consistency in the output. So I would like that every path actually maps to the same segmentation, and then I can backprop through and train everything all at once. And that is called imposition of path invariance among a network training, and it's quite a fruitful direction followed by Chixing Huang, who will probably give you more information into this. And time, right? So here we could basically analyze in the same framework many of the algorithms that are speaking of cycle consistency of time. So here we have a forward flow in time, but now because we have all the frames, we could go back and look and seek consistencies across observations, so consistency among the observation and the synthesis, for instance. Then what is synchronization in this framework I just described? Well, it is given relative maps this time, recovering the absolute quantities fi, a vertex labeling, right? So given relative maps, find a consistent vertex labeling. We can formulate it as an energy minimization simply. And this is, I think, a good look because many of us are familiar with such formulations. It's easy to explain, even though later algorithms use different formulations. So essentially what we want is that every cycle should be a null cycle, which means that if I take any vertex and trace all the relative transformations, I should map back onto the same labeling. Plus, well, there should be a data term consistency, right? Because this is very easy to construct. I can just construct these f's, so these f's such that this always holds. However, constructing f's that are also in alignment with what I have observed in these fij's while satisfying that is a difficult task. Indeed, it results in a non-convex program. So If my maps are group valued, I could make certain assumptions that they are invertible, or even if it's orthogonal, the inverse would be the transpose, for instance, and so on. And I can rewrite those energies in a different way, in a more compact way. And notice that in such case, if this is the assumption, well, I am also, by minimizing this alignment to the data, I'm also satisfying the cycle consistency of the graph as proven before. And path invariance is similar. It's just maybe it cannot be written in the form that you see in the second row. However, it could be written similar to the first one. It's basically what we want is the satisfaction of the data that I observe, plus I would like a path invariance. So regardless the path pair I take, I should arrive at the same labeling. So let's take the basic case of invertible linear maps. Well, just consider the energy that we have defined before, and just consider the case where ρ is an identity map. Well, in that case, this energy looks like a Dirichlet energy, and we seek to find a harmonic. And from a matrix point of view, using the analogy to graph Laplacian, for instance, which is heavily used in minimization of Dirichlet energies, well, we could see that we could construct such a G matrix that are composed of those relative maps, and we could consider a Z matrix that is just identity matrix added to G, and we observe that Z actually admits such a decomposition. Right? So this is regardless of which group we are working in, as long as it's an invertible linear map that would hold because of the cycle consistency constraint, which can be written in such form. Well, then this problem might turn, by choice of a certain D, into such a problem. This is heavily considered in synchronization of maps. And then we could make further assumptions. We could speak of the orthogonal linear maps. And these algorithms, by the way, they will be explained in more detail by Trishing and Federica. I'm just giving an overview of different strategies to minimize those energies. Well, let's consider the one where maps are orthogonal. In this case, the inverse would be equal to the transpose, and then with very basic derivation and expansion of this Frobenius norm, we could see that we could write this energy using the trace of such a matrix. And this can be rearranged into the semi-definite program, into such a program on which we could do a semi-definite relaxation. So we basically relax the group and speak of the G as a positive definite matrix with diagonal identity, and that is basically like a low rank decomposition, has a low rank decomposition. Right. And then we can speak of a spectral solution, and this time it considers the same problem, but with the constraint that there's an orthogonality. And this is highly related to the Rayleigh problem, and the solution is given by the eigenvectors of G. And this is used in many other domains, of course. And you'll see both SDP and spectral methods, they are closed form. So they don't need an initialization. They can solve the problem directly. And because of certain guarantees, that is. But then they do not satisfy the group constraints completely. Of course, we could have more constraints on F. Then in that case, this becomes a spectral relaxation. And then we have to project back onto the feasible set. So there are two ways to avoid this. One would be to use a constrained optimization, where, well, this is a difficult thing to do, of course, and the complexity rises. Or we could use a Riemannian optimization, which is unconstrained, but the steps are taken on a Riemannian manifold. So let us observe the latter and just speak a little about it, because constraint optimization is very case specific, I would say. Riemannian optimization, it basically uses a characterization of the Riemannian manifold, right? We are given a point X that could refer to the F's that we have been using, and we can speak of a tangent space, right? And all the constraints set, they define this manifold on which I'm trying to follow a geodesic path, which is characterized by gamma. And I can do that by use of the logarithm and exponential maps by mapping to the tangent space, taking a step in the tangent space and mapping it back. Right. So here is how a Riemannian optimization would look like. Let's take that problem, which I want to minimize over maps that are living on certain manifold. Well, here's an algorithm of a general Riemannian line search minimizer. Let me explain you here. So in this, at x, I could compute the Euclidean gradient, which is the gradient of the energy here. And I can use this, I can use the definitions of Riemannian geometry to project this vector onto the tangent space, obtaining a Riemannian gradient. And I can take a step along this gradient, having a new value, right? And then I can compute the gradient again, and I can project and follow this trajectory. Oftentimes, it's very hard to compute the true geodesic, especially for matrix manifolds. So in those scenarios, we could follow rather a retraction, which is an approximation of the true geodesic. And whenever the exponential map is fully available, we could also perform optimization along the geodesic. So this algorithm summarizes exactly that, with the addition that the step length here is determined by a line search rather than having a predetermined value. Okay, so the first part of the tutorial is over, where we have identified and worked on some basic problems in synchronization and looked into certain algorithms that characterize the solutions. And right now in the second stage, I will dig into another topic, which is quite interesting and which I have been working on recently, that are the uncertainties and ambiguities in real life. Because in real life, these observations, these maps, cannot be really computed in a truly correct manner. And many of the problems actually involve dealing with ambiguities, or at least estimating an uncertainty, quantifying how reliable a solution would be. So I will explain this first in the context of multiple rotation or motion averaging, and this will give us an idea of how we could derive a synchronization solver, and then how we can estimate uncertainty. And from there, I will move on to different maps, and finally, I will investigate a little bit of the neural network literature where recent works are mostly clustered around. So, okay, here's what a general camera pose looks like. It's composed of a rotation matrix and a translation vector, which together they live in the special Euclidean group. And rotation itself belongs to the special orthogonal group. Notice that the speciality comes from the constraint that the determinant should be 1, and strictly, and plus it's an orthogonality, right? And you could this group acts on a 3D point x as follows. And I will in general analyze R, but T will come from time to time, but just know that it belongs to R3, the translations, so it will be easier to deal with always. And rotations, I will be using quaternion representation to explain them. Okay, so here is the multiple motion averaging or rotation synchronization problem, right? So again, we take our cycle consistency constraint. Here it's written reverse. That's generally how it's used in the rotation convention. So this just changes from world to the camera point of view. And we are giving those relative maps, these MIJs, right? And we are seeking absolute camera poses with respect to one world frame, which is picked arbitrarily to reduce the gauge freedom, so reduce the degrees of freedom of the problem. Okay, so we are looking for these RIs and TIs essentially. Let me explain the quaternions just a little bit. I will give a quick recap, and the purpose of the tutorial is not to explain quaternions very deeply. So they are entities that extend complex numbers. So we are speaking of 4 quantities here, Q0 to Q3. So it's in 4D. However, they belong to a unit sphere where the antipodally symmetric points are identified with the same rotation, which means that Q and minus Q represent the same rotation. And there is always a map. Given a rotation matrix, I could go to the quaternions and I could define a rotation in the rotation matrix, like r times x, or with the quaternions using such a quadratic product. And then I can define a geodesic distance on the quaternion manifold as a simple operator of arc cosine. And there is a strict relationship with the axis angle representation, where the Q0 is encoding the cosine of the angle, and the rest of the quaternion is responsible with the axis scaled by the sine of the angle. Well, let's then find a simple classical rotation averaging algorithm, and this is given by Govindu, and it's one of the starters of the research in this domain. Well, I'm given the cycle consistency constraint. I can always write it in terms of quaternions, right? So there's a quaternion product here, and these are just representing the same thing. And we can use the adjoint of the quaternions to linearize it. So this is just a group linearization, and we can write it this way, where Qij is a 4x4 matrix, which is the linear version of Qij, and such form. If I have multiple observations coming from all the edges, I could actually write up a matrix and stack up all the quaternions that I would like to find into Q, and write this linear system, a homogeneous one, and solve it. Well, there's a closed form solution. It's nice and beautiful, easy to solve, nice to formulate. However, we cannot really enforce the group constraints, right? So there is no guarantee that what the resulting Q would be. And for that, just to have those constraints, we either go to semi-definite programming or spectral relaxation, but even those might not be enough for the case of quaternions, and if you want to satisfy it properly, then we have to go to Riemannian optimization. Well, we also want another thing. We definitely want to estimate the uncertainty, and whenever we speak of uncertainty, we speak of Bayesian methods, and we speak of distributions, because this is the natural and principled manner to quantify uncertainty. And luckily, there's the Bingham distribution that is very well suited to explain the manifold of quaternions. So it's a distribution on the sphere. However, due to the quadratic nature, as you see here or here, there's no difference between having a negative or positive here, and that's why it's an antipodally symmetric distribution, just like quaternions. And while the normalizing constant is a complex expression, we could always estimate it with some form of interpolation. Well, now I will present a framework that's called tempered geodesic MCMC that can do optimization, so that can solve the synchronization problem, and at the same time sample from the posterior of the problem, so that we could get uncertainty quantification or explore the possible solutions of the problem. So we are basically interested in two quantities. First, the maximum a posteriori estimate. This just comes from just comes from the Bayesian formulation, where we have a prior here. Otherwise, this is just the likelihood term, which corresponds to the synchronization term of the rotations and translations individually. We could just also consider the left part, where we seek the likelihood of the generated or the estimated of the estimated absolute maps to the data. Right? And then we are interested, of course, in the full posterior distribution. So solving the first part of the problem is not that hard, because it's an optimization problem and we have seen multiple ways to solve it. But the second part, where we want to explore the posterior, is not that straightforward, because now we are in a Riemannian manifold. And what we do for this, we use the recent advances in Monte Carlo and consider the Hamiltonian on the manifold. So here G is a Riemannian metric tensor, and this is just a modified Hamiltonian expression. And then we further modify it by introducing this beta term, and this will allow us to represent, well, this will allow us to do two things. First, by setting beta to an appropriate value, we could perform an optimization. And second, and setting beta to another value would allow us to perform sampling. So we are having one formulation here to perform both sampling and optimization. and this is what we choose to do so. Well, this whole thing, the system of this whole thing evolves basically with respect to these differential equations, and where p is the momentum and x is the position, and that really comes from the definition of the Hamiltonian, right? And here g is really the Riemannian metric, and everything is written on it, and the last term is a Brownian motion. So note that if we cancel out the Brownian motion, this is just a gradient descent with momentum, and that is just evolving the rotations here, the x, right, and solving the system. Whereas if we start introducing the Brownian motion to the momentum, we are basically to the gradients, right? We are now introducing some kind of a randomness, and that the algorithm starts to explore the posterior or the energy landscape, right? And this allows us to draw samples. Well, let's see the solution to the problem first. This is how the evolution would look like. Right. So, and this is how the uncertainty estimation would look like. Well, what we could do now for each given SFM problem, so we are given many images of the Dantes square here, and then we are trying to, through synchronization, find a reconstruction of the 3D, right? So here we are synchronize the relative poses in between images, and what we could see is that because now we have multiple solutions to this problem, we could just hypothesize, we could sample the posterior, each sample corresponds to a solution of the synchronization problem. Now we could assemble, well, we could basically assemble a color map here, where each color, if it's red, it corresponds to high uncertainty, and blue corresponds to low uncertainty, and this uncertainty we estimate from the covariance matrix built by the samples. And we can see, applying the same procedure to Madrid metropolis, we can identify that distant structures, which are hard to triangulate, are more uncertain, whereas the structure that is close to us is more confident. So this gives us a new probabilistic look to the synchronization problem, actually. We are given a Riemannian manifold. Well, this is like the constraint set where the parameters are living in. And then we are somehow given the analytic geodesic flow. Well, this could be in form of a retraction or not, or an analytic flow. And then we are given a suitable probability distribution. Given that, our algorithm will give you a knob which we could tune to perform sampling or to perform optimization. Well, we could extend this to other maps now. For instance, correspondences, right? So given correspondences, we can synchronize them plus estimate certain confidences for each correspondence, or for each, let's say, identification of a vertex by a certain label. So consider this problem now. Well, we are given, let's say, relative permutation matrices between two shapes, two images. These are just correspondence matrices, basically, where the number of correspondences, the number of elements are equal in both images. And we are looking for these absolute maps, these xi. So these are also permutations. As you see here, they belong to the permutation group. So we are looking to minimize this u, the potential energy, which is like just another form of synchronization that, as we have seen, right? Yet, this is a direct optimization on the permutations, and it's quite difficult, even with the Riemannian methods. It's not defined at all because it's a discrete thing. Well, we could relax it. We could relax it onto the double stochastic matrices, which are, instead of having ones and zeros, now the rows and columns are individually having a sum of 1. So this is a continuous relaxation of the permutations. And then now we can perform the optimization on the double stochastic matrices. So far so good. Well, we can optimize this using any Riemannian algorithm, like your favorite algorithm, Riemannian gradient descent, even more sophisticated ones like LBFGS or Riemannian BFGS. And we can devise now a sampling scheme for this, right? Just using the same ideas as we have used before. Now we derive a similar differential equation, so stochastic differential equation, again with some Brownian motion on the Riemannian manifold, and that we call a Riemannian Langevin Monte Carlo. However, the key here is we do not really have the exponential map for the manifold of doubly stochastic matrices. What we have is a retraction operator, is a first order approximation of the exponential map. Well, we could still use it, right? We could still solve this differential equation just using retractions. And the solutions, well, we start from a bad initialization like this one, and we come up with a solution, and you see like a matrix here of confidences, right? And this has to be diagonally dominant. Whenever we miss a diagonal, that means it's not a correct estimate, and red is denoting high values. So you see that sometimes we are missing the correct values, but then if we consider like top uncertainty, so instead of considering one solution but multiple solutions, then we can have some kind of a diagonal dominance, right? And same holds true for other data. Well, this is great, but now we can move on to the ambiguities, right? So this just considered uncertainty for two problems: rotation estimation and permutation synchronization. So now we can. So how do we handle ambiguities, basically? Well, it's the natural form, as we have seen, is to work with distributions. And on the left, you see a classical synchronization, where the maps that we want to find are marked in red, and the relative rotations are given in black. And we are given one relative rotation per edge and seek one absolute rotation per node, basically. Well, in an ambiguous problem, we really cannot have a single solution to the relative pose estimation. We really cannot have one M, but we should be speaking about a distribution over M, right? So for the case of a single entity, so single quantity, that rotation, that distribution would be a Dirac delta on the Riemannian manifold or the Lie group. Or if I have multiple rotations or multiple solutions to this problem, we could have, well, an empirical samples over a distribution, or we could have a continuous distribution involving those samples. So in this final part of addressing ambiguities, I will be considering edges that are labeled with probability distributions. If you like, you could say these are probability measures from an optimal transport perspective. So we are given those relative measures, these are empirical measures, and we are seeking the absolute probability measures, right? And these are exactly defining the distribution in the absolute node that we would like to have. So consider the classical synchronization on the right. So we have this Rij approximately equal to Rj times Ri inverse for all I which is not in J, which is not equal to J. Well, we could convert this problem now to a distribution synchronization or a measure synchronization problem simply by replacing the distances between rotations, or the geodesic distances, by the divergences between probability distributions. And as you see here, we have the absolute measures from which we could compute the relative ones, and then we are also given the observed relative measure, and we are seeking a divergence between them, and we are seeking to minimize this. So on the left, you see a classical rotation synchronization, as we have studied. And this can be solved by many algorithms that I have talked about, and you will be seeing in the rest of this tutorial. However, for this problem now we just introduced here, there is no solution. And what we propose in this paper is a way to solve this, basically using optimal transport on the Lie group of quaternions. And this uses geodesic synchron divergences, and we show ways how we could minimize it. In fact, we show a theoretical guarantee that we are able to find a global optimum of this problem under certain mild assumptions. So for the details, I refer you to the paper on the slide. So currently, some of the synchronization algorithms are actually differentiable, while some are not. And current neural network-based multiview processing engines, let's say, can use synchronization algorithms built in. So this is like building a deep declarative network where the optimizer is a synchronization module. So here in this example, we can formulate a robust registration where the weights of the robust estimator are determined by a neural network, and the estimator itself uses those weights to synchronize different views. And by that, we can have more robust registration. Or we could go one step further and build the synchronization into the neural network. And we could basically start from the point clouds, extract 3D features, and then from that perform the pairwise registration within the network and use a synchronization to come up with the final solution. And we can train this architecture end to end, and this generates so far the best results that we have seen, and this is basically a publication in this year's virtual CVPR. And finally, well, graph neural networks can actually learn to synchronize, and this can be made robust, and there are certain attempts doing it, and Neurora is one of those attempts where there are multiple stages of graph processing that lead to a more robust solution, and that is actually provably, like, experimentally demonstrated that the results that Neurora estimates are better than any handcrafted robust algorithm. Well, so where do we go from here, right? So basically, we need a complete treatment of uncertainty, and we need to be able to synchronize things in neural networks. So where maps are neural networks. Right? These are two obvious directions, but I am probably working towards a couple of directions which I have to share with you. The first one is synchronization without synchronization, right? So it's actually a tedious problem to solve, and if we can avoid it completely, we must avoid it. And the way to be able to do this, it goes from finding invariant embeddings. So we want to find such embeddings that are invariant under the group transformation that we are considering. Now, in this case, for instance, that we have partial observations, now we want to register them and put them together into a final bunny, right, as you see in the middle. Now, we could always find a distance matrix corresponding to each partial observation that is invariant under the action of SE3. And then we could basically merge them in one common distance matrix, which we could revert back using a classical multidimensional scaling algorithm to a bunny, to a full bunny, basically, right? And this is one way to kind of use canonicalizers, if you will. Well, we could use canonicalizers in wider contexts. Basically, we could have neural networks estimating those invariant embeddings, and then through these embeddings we can perform aggregation. And this is given in many works of normalized object coordinates. I don't have the citation here, but it's Hu Wang and Srinath Sridhar. You should be finding their work easily. Well, canonicalizers is certainly one way. How can we combine synchronization with canonicalizers in order to yield more robust systems? And finally, we could think of synchronization of multiple entities like motion and segmentation, for instance, and we could apply it to articulation in that way, right? And then really figure out robust solutions to estimation of kinematics and so on. Thank you for watching, and I wish you a good time in the rest of the tutorial as well. And please ask your questions to me either via email or in the dedicated Q&A session of CVPR.